In practice, the way we calculate changes in entropy is going to be related to heat flow into or out of a system. And this is shown by the Clausius inequality. It says the change in entropy in a system is going to be greater than or equal to the heat flow into the system divided by the temperature. And we can actually break this down into two statements. Since it's a greater than or equal to, we can say that the entropy change of a system is equal to the heat flow into the system divided by temperature for a reversible change. Or we can say that the entropy change of a system is greater than the heat flow into a system divided by the temperature for an irreversible change. And an irreversible change is one that is spontaneous. Okay. All right. Well, how do we deal with using this inequality here? Well, in practice, it's not a barrier at all. Let's go ahead and do this on the next page. Let's look at two different processes. And we'll draw them on a PV diagram. So we're going to start here at point A, go to point B, and we're going to do it two different ways. We'll do it with some sort of crazy irreversible process and with a nice reversible path. So we've got delta S1 and delta S2. And we've got the heat transfer that occurred in the first path, we'll call it Q1, and the heat transfer on the second path. All right, well, what we have to remember here is which things are path functions and which are state functions. Q1 is definitely not going to be equal to Q2. It's two different paths, and we know heat and work are both path functions, path matters. On the other hand, entropy is a state function, and that means that all that matters is the final and the initial state. And as long as those are the same, and they are here, then the two paths have to have the same change in entropy. And this means if I want to find the entropy change for this irreversible path, there's a pretty easy procedure. I say, okay, I want to find the entropy change for this path. I set up a path that's easy to calculate, but has the same endpoints. It's going to have the same entropy change. And so I can say that that delta S for path 1 and for path 2 are equal, and that path 2 is going to be the integral of the heat flow for that second path divided by the temperature. So we can actually always construct a reversible path if we have an irreversible process, and this is how we're going to calculate all our entropy changes. So let's look at two concrete examples. The first type of entropy change we'll worry about is what happens to entropy when there's a phase transition or a phase change. So maybe we're boiling or freezing. And in this case, and we could imagine taking some substance, maybe it's water and it's ice, and we're gonna melt it to form liquid water. Okay, so how do we calculate delta S? Well, we say, all right, we're going to go from solid to liquid and integrate. Left-hand integral, delta S. What about the right-hand integral? Well, when we go through a phase change, we know that the temperature doesn't change. If we melt ice, we have to stay at 100 degrees, at 0 degrees C until all the ice is melted. So the temperature is a constant. We can just pull it right outside that integral. And so we just get Q over T. And when we go through a phase transition, the pressure is constant as well, right? When we melt ice, we do it at 0 degrees C in 1 bar. So if the pressure is constant, we can equate the heat with the enthalpy change. In this case, the enthalpy we're talking about is the enthalpy of fusion. And the temperature we're talking about is the melting temperature. And we could do the same thing for vaporization or for any other phase change like this. Oops. Let's go. Let's cross this whole thing out. We were looking for the entropy change, and that's just the enthalpy change divided by the temperature. All right, so those phase transitions are pretty easy. What about when we don't have a phase transition? What about a process where we've got a temperature increase? So let's imagine we take water again, and we're going to take liquid water, and let's do it at 298 Kelvin, and we're going to go to say 350 kelvins, and let's do it at I don't know, 2 bar. All right, well, we construct a reversible path from this endpoint to this endpoint, right? Because we have the pressures are the same and we've just changed the temperature. And once we've constructed that reversible path, you can see it would be a reversible isobaric path. We get this. ds is equal to dq over t. And we integrate both sides. And that's a very ugly integral sign. Okay, we get delta s is equal to, well, wait a minute, we can't pull the t out because we explicitly said that t is going to be changing. So in this case, we actually have to do the integral. So how are we going to do that integral? Well, we need one variable. So we need to put everything in terms of t. Well, the first substitution we can make is that if we're working at constant pressure, we can replace dq with the enthalpy. And then we can say, okay, what can we replace dH with? We can always go back to fundamentals and remember that dH is equal to Cp dt plus mu t dP. But wait a minute, we're working at constant pressure over here. So that means this term here has to go to 0. So we can just replace dH with Cp dt. And we have to remember we're integrating from some low temperature to some high temperature. And at this stage, we either have to look up what Cp is as a function of temperature, or if it's a small temperature range, we can just pull it out and assume that it's constant. If we do that, we're going to get Cp log of T2 over T1. So that's how we would handle heating at constant pressure. If we were doing it at constant volume, it would be a similar answer, except for we couldn't make this substitution, right? Because at constant volume, heat is equal to internal energy. So this would end up being CV dt. Other than that, it would be the same.